Okay, good afternoon. Let us start our lecture. So last week we talked about independent events. So if we have more than two events, we can have n independent events. But there are two types. One is just pairwise or pairwise independent events. So in this case, any two out of the n events, all right, they are independent. So in other words, probability of AI intersect AJ, AI and AJ occur together is equal to the product of the two probabilities of AI occurs and probability of AJ occurs. So this is called pairwise independent. But usually we would like to have this mutually independent events. That means all n of them are mutually independent, which is a much stronger conditions. All right. So in this case, it means that for any subset, any two of them are independent, any three of them are independent, any four of them are independent, and so on until all are considered as independent. All right? So we have this result. Any k of them occur together or simultaneously with a probability equal to the product of individual probabilities of all these events. All right? So we can replace by one of them by their, or any one of them by their complement events. That means if we have AI or A1 up to AN are mutually independent, then if you replace any one of them by their complement, then the set of events are still mutually independent. All right? So what I mean is that if all these are independent, are mutually independent, then if I replace this by A2 complement, then this bunch of events are also mutually independent. So we talk about examples. So the first two example one indicates that there are events that are mutually independent and also pairwise independent. All right. So this is example one. Now, in this example, the way that we compute the probability of A intercept B or probability of A, all these are based on counting. We count the number of possible outcomes that favor to A or favor to B or favor to A intercept B and so on. So we show that the pairwise, they're independent. Not only that, they're also, this one also independent. So combining all these facts, altogether we have only three events. So any two of them are pairwise independent and also the three of them are independent. So they are mutually independent. All right. Example 2, we define a slightly different event C. And now these three events can be shown. They are they are pairwise independent. But unfortunately, they are not mutually independent. Why? Because the probability of A intercept B intercept C is equal to 0, which is not the product of probability of A times probability B times probability of C. All right? So that's where we stopped last time. All right? Now, so another example, so we have three fire engines operate independently. That means whether one engine works or not has nothing to do with the other engines. So that's what we mean by independently. So probability that a specific engine is available, so this one is available, a particular machine is available with a probability, it's available when needed is 0.9. So we are asked, what is the probability that no engine is available when needed? Now, in order to answer the questions, you must able to identify the events. Identify the events, and if possible, get the probability of these individual events or something related to it, and then also translate the question into a probability involved events that we defined. So in this case, we have 3 fire engines. All right. So very easy to define. We can let AI be the ith fire engines that is available where it's needed. All right. So this is the event that the engine is available. It's the ith engine that is available when needed. Okay, I have to include this part. All right. Okay, so with this, then how am I going to translate the question into events involve A1, A2, A3? So no engine is available. To translate it means what? So means A1 complement, A1 is not available, A2 is not available, and A3 is not available. So we need all these 3 to happen together. Am I right? No engine available. That means A1 is not there when I need it, A2 is not there when I need it, and A3 is not there when I need it. How to combine these 3? Intersect or union. So this, I need all this to occur, so I need the intersection. So basically the question is to ask, what is the probability of this? Am I right? And this is important. You must able to translate the question into a probability statement, involve the events you defined based on the information given to you. All right? So, what is this 0.9 then? Is probability that the machine available. So its probability of A1 is 0.9. How about A2? Is it 0.9? Is it 0.9 also? Why? Why is it 0.9? Because it says that probability of a specific engine available when needed. So these specific engines can be A1, can be A2, can be A3. Unless you are told that these 3 machines are different. If they're different, or different probability, what I mean is different probability, then they will tell you. Otherwise, we understand that it means A1, A2, A3 have the same probability of available when needed. So each one is 0.9. Then how about this one? The first 2 machines, or A1, or the first one, the second one machines are all available at the same time. So what is this probability? Is it 0.9? Is it 0.9? Or 0.9 plus 0.9? Or 0.9 times 0.9? Or 0.9 divided by 0.9? Just multiply. Or 0.9 minus 0.9, right? But you must be able to answer why. Is it 0.9? Why not? I see only one number, 0.9 there. Because 0.9 refers to one particular machine available when needed. Now I want 2 machines to be available at the same time. All right? So, do we know that? Do we know this probability? Do we know? Is it given? No. It's not 0.9. Other than 0.9, then that means you have to work on it, right? It's not given. So it is not 0.9, then is it 0.9 plus 0.9? Yeah? A1 available with probability 0.9, A2 available with probability 0.9. Add them together. So both machines available equal to 1.8. No one laughs. How can a probability be 1.8? So must be wrong. All right? You cannot just add these two numbers to probability. In fact, what you are asked is to find is the probability of both events occur. All right? So we don't know, except if, a big if the two events are independent. This is important. If they're not independent, then you cannot work it out. So this one is equal to probability of A1 times probability of A2 only when A1, A2 are independent events. So that's why I told you in the last lecture that independent is a very wonderful property if you can show or you have events that are independent. It makes life easy. Otherwise, you are not able to compute what is the probability of A1 intersect A2. Then nothing for you to count. No outcomes for you to count. No these sample points for you to count. So in this case, it's the product of probability A1 times probability A2. So it is a 0.9 square. But that's not what we're asked to find. We're asked to find this one. So now the question is, are these independent? Yes, of course. They're independent. So it's equal to probability of A1 prime, probability A2 prime, probability of A3 prime. Do we know this one? Yes, we can compute it. It is just 1 minus 0.9. All right? All right? 1 minus 0.9 and 1 minus 0.9. It seems not right, right? Okay. So you multiply them, so you got 0.001. So that is the probability of none of the machines available. All right. So come to think of it, maybe I should include more engines. Let's say if I have 5 engines, I have 5 engines. Then when I need one, then the chance of getting none of them will be 0.1 raised to power 5. All right? So it's a very small probability that you will not have any. But let me ask you, I increase the number of fire engines. Of course, will make the probability of no engines available is smaller. But how about if I want to reduce this probability of no engine available when needed? Besides increase the number of engines, what can I do to have an even smaller probability? All right? So here I have 3 engines. No engines available, the probability is 0.01. So I increase the number of fire engines to 5. Then the probability reduced further to 0.0001. So now my question, besides increase the number of fire engines, what else can I do? So maybe not under your control, is to increase the chance of the engines available. How to make it higher chance of available? Try to stop those unnecessary call. It's no fire, but then maybe some problem. I cannot open my door and call, and then fire engine arrive and help me to open the door. Call a locksmith. So educate people so that make sure that the chance of a fire engine available when needed is higher, and not because of some other missions that they were used or not available. So my point is, look at how we obtain it. So if I want to reduce this probability, one is to increase the number of engines, right? That means money. You need to put more money to buy engines, fire engines. The other one is try to get the probability of the machine available as higher than 0.9. Let's say 0.95, then your chance of no engine available may be smaller. All right? Okay. So here's another example. A grader will mark with a marking error for particular questions with 0.05. All right? And if there are 10 questions, and questions are marked independently. So you see, this word, independently, appear. So what does it mean? It means that altogether, you can think of it as you have 10 events. Why 10 events? Because you have 10 questions. And what we're interested is whether a particular question is marked wrongly. So that is an event. So A1 represents the event that the first question is marked wrongly, and so on. So what's the question? What's the probability no errors are made? No errors are made. So that means all 10 questions are marked correctly. All right. Then at least one error is made. Now, if you pay attention to these two events, the first one, okay, you have 10 questions. So what are the possible number of errors? 10 questions. Right? So you mark all correct, 0 errors. You mark out of 10 questions, maybe 1 mistake, so 1 error. You can have all 10 wrong, right? So that means no error, 1 error, 2 error, up to 10 errors. All right, the number of errors. So these two events, A and B, the first one is error equal to 0. That means no mistakes. The second one is at least 1. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wow. You have to have any one of these events or a union of all this. All right. So in fact, what I'm trying to say is that this may be just complement of each other. All right. The third one question is that if there are n questions, so no more 10 questions, but a general number, n, and the probability of error is p instead of 0.05. So give an expression of these two probabilities. All right. So in other words, you cannot rely on your calculator. Your calculator cannot do symbolic calculation. So you need really to understand the questions and try to derive the answer. Okay, so let's start with some concrete number first. So n equal to 10 and p equal to 0.05. All right, so we write down our event. EI be the event of making an error in the ith questions. So we have E1 up to E10. And they're all independent. All right, no error means that it is E1 complement, intercept E2 complement, and so on. So it's equal to, now this part is just trying to answer the question, and this part from here to here, we make use of the independent properties of all this. Why is it independent? Because we are told that marking of each question are independent. But come to think of it, it's not a very good assumption. Am I right? Yeah. So tired, marked it wrongly for first question. So it's likely you have a higher chance to mark wrongly in the second question. So what I mean is that the independent assumptions may be some, we may doubt about this assumption. But for this question, we are told. So we don't have to worry about it. So we are told that they're independent. The marking of this are independent. So we just multiply them. So get the answer. The answer is 1 minus the probability of mark it wrongly raised to power 10. So this is the answer. So intermediate, immediately I know the answer for part C. So it is 1 minus P. P is the probability of making an error. 1 minus P is no error raised to power n. So that's the answer for one part of the answer for part C. Okay, second part, at least one error. All right, now at least one error. So it means that it is the probability of first one wrong, or second one wrong, or third one wrong, up to this. All right. Now, if you recall, we have discussed about something called inclusive and exclusive principle, I think. Inclusion and exclusion principles. So this one is equal to what? The sum of probability of EIs plus the sum of probability of intersection of two, and then minus, and then plus probability of the intersection, all those probability related to 3. I even hate to write it down, so complicated. I from 1 to 10. Minus summation probability of EI intersect EJ, where I is less than J, and so on. Or not, I not equal to J, and so on. Wow. Think about it. So many terms that you have to evaluate. So we try another way. Okay? So in fact, if you recall, this one is nothing but just equal to is equal probability of the complement of all the intersection. Complement. All right? So what is this? This means that, I'm so sorry, complement of, intersection. All right. So, at least one error. What is E? E is making error. All right. So union of all this is equal to the intersection. Sorry, I made a mistake here. It's equal to this. All right. Intersection of all these complements. So complement of it. Or 1 minus. All right. So at least one error means that it's the complement of no error. No error, the complement is at least one error. All right. So that means no error, one error, up to 10 errors. So this part are at least one. So this is a complement event of all this. So it's equal to 1 minus 0.95 times 10. So from here, we also can write down the probability will be 1 minus p power n. It's 1 minus p. All right. Okay. So that's chapter 1. Good. Now, try to do different things. Random variables. Chapter 2, random variables. Do you know what is a variable? What is a variable? Variable, that means it varies, right? And what is the opposite of it? Constant. Never change the values. You study algebra, right? Algebra, we have x variable. All right? But in probability, we have this random variable. So, random variable is a special type of variables. So it has the property that it takes on a range of values. On top of this, it also have another quantity or numbers associated to random variable. That is how likely the random variable takes these values. In algebra, we just, okay, x is a variable, so x takes any values over the real line, all right? But it does not have another quantity, is how likely the variable takes certain values, all right? So a very simple example is like I toss a die. So there are 6 values, 1, 2, 3, 4, 5, 6. I toss it, and then I look at the outcome. So the outcome can be 1, can be 2, can be 3, can be 4, can be 5, can be 6. All right? On top, I also try to link these values with a number called a number that associates to how likely they will get these values. Now, if it's a fair die, then chance of getting a 1, getting a 2, getting any of these 1 out to, up to 6 numbers, probability is 1/6. All right? So a random variable is a variable, so have a range of values. And then it also associates with each value a probability or a probability measure or associated with it. All right? Now, so suppose now I have a die, also 6 faces, but each face I paint it as 1. 1. All 6 are 1. No matter how you throw, 1 always show up. Is it a variable? The outcome, is it a variable? No, it's always be 1. All right? So that's a constant. No variable. So whatever you do, the outcome will be 1. No matter you throw it up, all right, throw it behind, the outcome is always 1. Because all the faces are 1. So my point is, first of all, a variable, if it always takes only 1 value without any change, it's a constant. It's not a variable. All right? So it's a variable, must have a different values. And associated to it, there should be a probability, a number that shows how likely it will take that value. Okay, here it is. We are going to discuss random variables, and we are going to discuss about the behavior of the random variable. There are 2 families. One is discrete probability distribution. The other one is continuous probability distribution. All right. And then we talk about cumulative distribution function and expectation. Finally, something called Chebyshev. I think it's S. Chebyshev inequality. It doesn't matter because this is a Russian mathematician, so when he convert it to English, different way to convert it. All right, now let's begin our journey of random variables. So it's frequently in the case that when the experiment is performed, we are interested in some functions of the outcome. All right, as opposite to the actual outcome. Toss a die. So usually we are interested in the face, the value shown on the face, top face. All right. How about toss a coin? Toss a coin. So the outcome is either head or tail. Yeah, just the face up. All right, head or tail. Toss 2 coins. Then we may have 2 heads, 1 head, 1 tail, or 2 tails. So these are the outcomes. All right, but I may interest in, instead of the outcome of whether 2 heads, 1 head, 1 tail, I'm interested in how many heads if you toss 2 coins. How many heads are there? So in other words, I toss only 2 coins. So the number of heads is either 0, which corresponding to the outcome are 2 tails, or 1 head, 1 tail, then it means that the number of heads is 1. Or that 2 heads, then the number of heads is 2. So instead of looking at the individual outcomes, now I use interest in number. And this number represents the number of heads in tossing 2 coins. So here's another example. Suppose I test 100 electronic components. We are concerned about the number of defectives that occur. Right. So we have 100 components. So each one may be a defective. So we want to know how many are there. So it can be 0. That means all are perfect. Maybe 100. Maybe all are defectives. Or maybe a number which is between 0 and 100. So of course, we also like to know what's the chance related to each of these numbers. So what's the chance that no defectives out of this 100? Or what's the chance that 50 out of this 100 components are defectives? So we want to know about this probability. Okay, so flipping a coin, we may interest in the number of heads, but don't care about how the head-tail sequence that we have. All right. That means if I toss it, so it can be like this, can be like this, can be like this. All right. These are just some of outcomes. Toss it 3 times. All right. But this one and this one, although the sequence are not the same, so it represents different sample points, but in terms of the number of heads, both are 2 heads. 2 heads. They have 2 heads. All right. So we don't bother about the sequence, but we just want to know the number of heads. So here comes. So in this case, it will be HHT, then TTH, THT, HTT, and TTT. So altogether 8 possible outcomes. In terms of number of heads, so there are 3, 2, 1, and 0 heads. Right? 0 heads corresponding to this one. So now the question here is, okay, how likely we see a 0 heads when we toss coins 3 times? How likely you see no heads? How likely you see 1 head? How likely you see 2 heads? How likely you see 3 heads? Are all these probability the same? Are they equally likely? Yeah, it's a bit confusing, right? Then how about the sequence? How likely we see head, head, head? 3 heads. How likely we see head, tail, head? Are they the same probability? Are they with same probability? Yes. All right? You see, the problem is that once you consider the sequences, so each of these sequences in fact are equally likely. So that's why they are important. We have to assume that they're equally likely. But not 0, 1, 2, 3. Because 0 corresponding to only 1 sample point. That is tail, tail, tail. How about x equal to 1? That means 1 head. This corresponding to 3 sample points. What are these 3 sample points? All right. Head, tail, 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 head, tail, and tail, tail, head. All right. 1 head. There are 3 sample points that give you 1 head. So in other words, they are not equally likely. So it's important that you have to know what are the sample points or events that are equally likely and what are not. Okay, go back to some simple one. So this is the sample space associated with tossing 2 coins. All right? 2 coins, 2 coins. Remember, if you want to have equally likely, then these 2 coins must be identified. You may have color, 1 red, 1 blue. All right? The first entry in this pair is referring to the red corn, and the second one referring to the blue corn. So that all these are equally likely. If you don't distinguish it, then these two, when you toss two corns, these two seems to you is the same outcome. But in fact, they may come from different outcomes. The first one may be referring to the first corn is head, while this one referring to the first corn is tail. So they're different outcomes. All right. Okay, so we define random variable. A random variable basically, the definition is a function. Hey, do you know what is a function? What is a function? Or y equal x squared is a function. But what is a function? Function, in fact, is just an ordered pair. Take one value and get the image. So it's something like this. Usually, okay, you have a set here. A set means that it's a collection of elements, and you have a set here. So for random variable, this usually is the set of real numbers, or a set of integers. So anyway, it's a set of numbers, all right? Then this one is our sample space of a particular experiment, all right? So in this example, this one has only 4 elements. So a random variable is to map one outcome to a value here. So that is a function. So in other words, we try to pair them, one from sample space, one from the real number. So for example, I will have from the sample space, this H, I will map it to 2. HT, map it to 1. TH, map it to 1. TT, map it to 0. All right? So it's mapping. That means HH will be T. HT will be 1, TH will also be 1, and TT will be 0. All right? So this is my sample space. This is the real number. So this is the function, x, to map all this. So this x, in fact, is the number of heads, the number of heads. All right? So usually written in this way. This is the function, map any elements from this set to any elements from this set. It can only map to one element in the range or in the second set. You cannot have HH map to 2 and also map to 1. HH can only map to 2. So this is all the results. All right? So it's a very simple example of a random variable. We map the sample space to a set of real number. Each element in the sample space, I give a number. All right. Now, can I do this? 3. And one of them mapped to this one. Or in other words, in the sample space, I have 4 sample points. In the real number set, I take 4 values. So I define a function like that. Right? Is it okay? Oh, confusing, right? Okay. The answer is yes, it's okay. But, a big but. You cannot interpret it. All right? Right now, the first example that I give you just now, the x has meaning. It represents the number of heads in the 2 toasts. If I define it like this, in the latest one, I add x equal to 3, add an image 3, and if you have th, then map to 3. That is also a mapping. But the problem is that you cannot interpret. So now your x does not represent the number of heads. It does not represent anything. All right? I mean, or you cannot describe it easily about what it means, what this random variable means. All right? Okay. So, tossing a pair of fair dice, x is the sum. X is the sum. All right? So in this case, we have 36 possible outcomes. Right? We have a pair of dice. So 36 of them, I map to the sum. So the sum should be from, can it be 1? No, right? The sum has to be 2 up to 6 plus 6, 12. So the range for this one is from 2 to 12. All right? So the mapping, this is how the mapping, this is a function, map a particular element in this sample space, which should be represented by an order pair. The first value, x, represents the outcome of the first die, y, the second coordinate, represents the outcome of the second die. So an example of an element here is something like this, 4. That means the first die is a 3 and the second die is a 4. So the mapping, the function will map to 3 plus 4 means 7, which is what we mean by the sum. So in other words, if you see a 3, 4, it will map to a 7. If you see a 2, 5, it also map to a 7. If you see a 6, 1, also map to 7. All right? So this is the mapping through this formula. So this is the mapping. All right? And these are the range. The random variable takes the value 2 to 12. And this random variable has a physical meaning. It's the sum of the two dies. All right? Here's another example. We toss a coin until a head occurs. All right? So, x be the number of trials required. So I tossed it one time. I got a head. So, okay. These are possible outcomes. I tossed it, it's a head. I stopped, I got a head already, right? Okay, if I toss it, a tail, I have not got a head. I have to toss it again. If it's a head, I stop. If not, I continue. Continue. Will you see something like this? Huh? No, of course. Once you got a head, you stop. It's go back to this one. All right? So in other words, the possible outcomes, or in this sample space, will be, how many of them? Infinite number of them. All right? It can be t, this is 4t. So this one means that it goes to infinity. It can be many, many, many times. If you're so unlucky, you toss, keep getting a tail, all right? So you just see tails. All right. X represents the number of trials. So this will map to how many trials? 1. This one, how many trials? 2, 3, 4. So in other words, I will map X of any element S to this equal to the number of trials. So I can give you examples only. So if you have this one, then map it to 4. Because there are 4 trials before you get your first head. All right? So then ask, what is the range for this random variable X? From 0, 2, 3, 4, up to infinity. Up to infinity. All right? Yeah. So it's not 1, 2, 3, 4, 5. These 3 dots are very powerful. It represent from 6 onward up to 1 million, up to 2 million, up to 1 billion. So represent by these 3 dots. All right. So now we go to a formal one, random variables. So let S be the sample space associated with an experiment E. That means they are doing something and there's an outcome, a bunch of possible outcomes. So a function X which assigns a number to every element in S, and it's called a random variable. All right, assign every element. X is a real value function, which means that the image has to be real number. The example that I gave you just now are integers, but it can be real numbers. That means it can be fraction, can be any real numbers. So the range space of X is the set of real numbers such you can find an image in the sample space. All right? So each possible value of X of the random variable, capital X, represent an event. Because it represents a sample point which means an event. Right? If S is the elements themselves are real numbers, then we just map it to itself. All right? So just like toss a die, the outcome are 1, 2, 3, 4, 5, 6. So I toss it, so the outcome represent by this number 1, 2, 3, 4, 5, 6. So my random variable will also take the value 1, 2, 3, 4, 5, 6. All right. But toss a coin, then I'm talking about, for example, number of heads. Then I have to link the random variable values to the outcomes. So that's why you see just now in our examples here. Go back. Okay, this example that we just mentioned. All right. So at first, there are only 0, 1, 2. It represents the number of heads of the tossing two coins. So suddenly, if I add this one represents H, TH, and does not have any meaning. I just map to this number. All right. So this random variable with this mapping is not very meaningful. So the actual one is the number of heads, which is supposed to be just 0, 1, 2. Only 3 values. All right. So this equivalent events is try to link the random variable. All right. I told you random variable is just a variable, so it takes certain values with a probabilities. But we try to link this to some experiment so we can appreciate what it means. All right? Like when I say the number of heads for tossing two coins, then we know that it's referring to the experiment of tossing two coins, and the outcome represented by head, 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 tail, tail, head, or tail, tail. All right? So these are the sample, these are the outcomes. And we try to link this random variable, certain values, to these outcomes of the experiment. So if the two are the same, we call it equivalent events. So here it is. So E is experiment with S as the sample space, and X is a random variable. Or X is a random variable at S to R. All right. So such that XS equal to certain values. Let me call it little x line. All right. Okay. Now, B is an event with respect to Rx. And B is a subset of Rx. Rx basically, okay, maybe more concrete. S, H, HT, TH, and TT. All right? So the Rx, the range space for this random variable is 2, 1, and 0. So it maps like this. All right? So it's Rx. So here, let B be an event with respect to Rx. So in other words, it will be a subset of Rx. So B can be 0, 1, 2. B can be 0, or can be just 1. Or B can be 1 and 2, or 1 and 2. All right? So solar is a subset of Rx. So now, suppose A is defined as A, yeah? I'm sorry if you're not familiar with the set language, try to understand it. A is a set. That means a collection of things. And what are the things inside this set, this event, or this set? It is those outcomes belong to the sample space. All right? Belong to the sample space. Such that it's not any outcome. Such that the sample, the random variable work on this sample points, you can find it in B. You can find it in B. All right? So if I go back, okay, let me repeat this. A is a collection of something. A is a collection of the sample points from the sample space. So when I got this S, little s, so I look at the Rx, look at the B. I try to look for those in B. B are real numbers. Look at the B. Take a particular number in this B and try to see what are the sample points in the sample space that map to this number. So for example, in the tossing two coins, if my B is just 2, then I look at all those 4 outcomes in tossing two coins, which lead to this 2. There are only 1, that is hat. Then A will be hat. So in other words, if my B, I'm referring to the tossing two coins examples, if B is 1, 2, for example, then I can find S referring to, in a sample space, this one and this one will give me 1. And this one, okay, maybe I should reverse it. So H will give me a value 2. Because this X represents a number of hats. So this give me 2 means that 2 hats, so referring to this one. This means 1 hat, referring to this and this. So therefore, will consist of H tail and tail hat. So this is my A. Why I have to do that? It's very important because we learned in chapter 1 how to compute the probabilities of events from the sample space. All right? We learned a lot. So now we're working on the random variable. So I must able to understand when I say the random variable takes a value B, takes the elements in B. So I want to compute the probability of this event B. So I must link up this B with the actual experiment, link up with the sample space. So that's why I need to find what I call equivalent events. So we have 2 events. One referring to the experiment, to the sample space. All right? So the other one is the values in the random variable. So I take a subset of it, B, I call it. Okay, so I want to ask, what is the probability of this event B? So I must look at each element, each value of this random variable, get back to the sample space. How many of them, what are the events, or what are the points that link to this one, to the elements in B? Then that is considered as an equivalent event. All right? So then this is why we want to know equivalent event. Then these 2 probabilities are considered the same. Equivalent in the sense that they are representing the same thing. When I say, okay, toss 2 coins, all right, the number of heads is 2. That means X equal to 2. The random variable, it takes the value 2, which is equivalent to having an outcome which is hat. All right? So these are considered 2 equivalent events. Okay. This one is an example, just mentioned. All right? This one means 2 hats. This one means 1 hat. This one means no hat. This one means 1 or 2 hats. All right? Fine. But this one, this is an event. You can find it in the sample space. All right? It's a subset of the sample space, HH and HD. But you cannot find an equivalent event in the random variable because it does not correspond to the number of heads is 2 and 1. Because number of heads equal 2 or 1 will include TH, which is not here. So we don't have TH. So it is, so in other words, this particular event cannot find, you cannot find an equivalent event in the random variable x. All right. The random variable x is defined as the number of heads. Okay? So in order to compute these probabilities, then you just have to convert it to compute the probability of A1. So this is the probability of having head. All right? So in that case, it's one quarter, and so on. So my point is, for the sample space, if the sample points are equally likely, then you can work out the probability of any event. While for random variables, we try to link up to the outcome of the experiment or link up to the sample space, but it's not necessary that you will always find something from the sample space that map have an equivalent in your random variable. Like in this example, HHHT is an event from this experiment. All right? How to describe it? Very simple. Two heads. How to describe HT? The first one is a head, second one is a tail. That's it. All right? So exclude. The first one is a tail and the second one is a head. I describe it. All right? But once you look at X, which is the number of heads, I cannot have something that is equivalent to this one. Because when I say one head, it covers HT and TH. So it's not the same. All right? So I want you to appreciate this. Okay, I try to summarize my random variable X. Okay? Remember, I need two things. Random variable must be a variable. So it takes values, more than one value. In this case, it's 0, 1, and 2. And associated to each value, there should be a measure of how likely it is. So in this case, I have 1 quarter, 1 half, and 1 quarter. All right. So it's 2 parts. All right? So that tells us everything about this random variable. What are the possible values? And what are the probability associated to each of these values? All right, so let me ask you. So we have tossed the coin twice. So we have this. Let's say if I toss it 10 times, right? And X represents the number of heads. So what are the possible values of X? From 0, no heads out of this 10, all right? 1 head, 2 head, up to 10 heads. Then you have to work out the probability for each of these values. Do you believe that they're equally likely? Obviously not, all right? So I construct a table with 11 columns, corresponds to 11 values, and try to work out the probability. Okay, fine. Now let me ask you, if I toss 100 coins, all right? How many heads? X represents the number of heads out of this 100 coins. All right. Or what? So maybe make it better to 100 times. I'll toss it 100 times. So I use the table. So I have 101 columns. I have to work out the probabilities. Writing 101 columns, 0, 1, 2, 3, a lot of work there. Let's say if I have 1,000 coins, I toss it 1,000 times. Right? Headache, waste of time. So my point is that, is it possible to express this probability using a mathematical expression or a formula? All right? So here it is. If X is the number of heads, X equal to the number of heads, by throwing the coin n times. All right? So X takes the value 0, 1, 2 up to n. In this example, n equal to 2. So the probability of x equal to a particular value is given by choose x out of n times. X means the number. So if P is the number of hairs, probability of getting a hair, then this one will be x times. Then number of tails, 1 minus P, n minus x. In this example, P is just half. A fair coin, the chance of getting a hair is half. The chance getting a tail is 1 minus half, so it's half. So this is a formula. And the formula, we'll come back to this in the same chapter. So this formula only valid when x equal to 0, 1, 2, up to n. Up to n. All right. What I'm trying to tell you is that, yes, there are two ways to represent, at least two ways to represent these random variables. All right. One is a table form. Gives you the values of this x random variable and also the corresponding probability in a table form. But I'm trying to tell you is that what happens if there's so many possible values for this random variable x, then your table will be very, very large. So we would like to have a neat way to represent it. So we use a formula, a mathematical formula. And notice that this formula only valid for x equal to 0, 1, 2, up to n. Beyond that, the formula is not valid. Is this formula valid for x equal to 1.5? Huh? It's valid? The one that I wrote down there? Okay, forget about the formula. Let me ask you, I toss a coin 100 times. What is the chance that I got 1.5 head? Right? What's the chance? I don't know. No, you know. I even ask a kid, they know. How can you got 1.5 heads? It's either 1 head, 2 head, must be an integer. So the probability of getting 1.5 head is 0. All right, so we cannot use this formula. The formula only valid when x equal to 0, 1, 2, up to n. Not even beyond n. N plus 1 that's not valid. How can you toss a coin 100 times and you got 101 heads? No, impossible. And sometimes use of common sense. Don't apply the formula blindly. All right? Okay. So, here it is. So, now how about a pair of fair die? What is the chance that the sum is 3? I think I can skip this one. So, in fact, this is the probability of getting different values. So you can work it out yourself. Okay, discrete probability distribution. So I told you just now, it just gives you an idea what random variable is, how we link up the random variable with the sample space. Okay, so now we look at different families of probability distributions. Just now the example that I showed you is called binomial distribution. All right. So now we try to, instead of going to a certain specific distribution, we look at a more general distribution. There are two families. One is called discrete probability distribution, and the other one is called continuous probability distributions. Okay, they have slightly different characters, right? But basically, we also have to answer a similar question. What's the chance that x takes certain set of values, things like that, all right? Or what's the expectation of x, all right? Why we have to distinguish between discrete and continuous probability distribution? Because the mathematics, the approach to find the probabilities may be different. In fact, they are different for these two types, discrete and continuous random variables or probability distributions. So what are these? Start with discrete random variables. So x is a random variable so long as the Rx, the range of space, is discrete, is finite and countably infinite. All right? That is considered discrete. Usually, a lot of times, it's just integer. But the definition applies to a finite range, all right, and or countably infinite. All right? I asked you this before. Do you know how many points between 0 and 1? No one knows. Infinite number of points. Infinite number of points. All right? Then, infinity seems to be a very, very abstract concept. And even worse, there's something called countably infinite. And what's the other one? You cannot count. All right? Obviously, from the word count. So, 1, 2, 3, 4. Count. You can keep counting. That is called countably infinite. All right? 1, 2, 3, 4, 5, and so on. Uncountable infinite, that means you cannot count. Just like how many pawns are there between 0 and 1? You cannot count. All right? Because always, no matter what 2 pawns that you take, we can always find a 1 in the middle. So you cannot count. So it's uncountably infinite. So you just bear in mind that, all right? Discrete basically is saying that your x values is basically is finite. Even that infinite, you can still count. All right? Still count. You're able to count them. That is discrete. So, since they can be counted or they're finite, I can represent it by x1, x2, x3 up to some number. Or continue until infinity. So a probability function, okay, for a discrete random variable is for each value of the random variable, I assign a probability to it and represent by f of x. So in other words, all right, this f of x, all right, f of x is basically the probability of the random variable equal to x. That is f of x. So now I put these two together. One is the value of the random variable. The other is the probability that it takes this value. And collect all these pairs. And that is called a probability distribution of the random variable x. Let me put it this way. If you have a random variable, if you know the probability distribution of this x, then you know everything about x. You are able to compute the probability of any event related to this random variable. So what is this probability distribution? So here it says that it's a collection of all the pairs, the value of the random variable and the corresponding probabilities. And you collect all these values. Each value of the random variable, you have the corresponding probabilities. So it's the set, a collection of all these pairs. So that is the probability distribution. All right? So the probability functions satisfy the following conditions. Each one has to be bigger or equal to 0 for all xi, for all the values of this random variable. The f of x, that means the probability x equal to this particular value xi must be greater or equal to 0. Secondly, the sum of all the probabilities, this one, sum of f of x, I, sum over I, this means what? This means that f of x1 plus f of x2 plus up to f of xn plus continue. All right? All this sum up to 1. Each is a probability. So sum up all this probability equal to 1. All right? These are important. This these are the properties for probability functions. So, in other words, for example, if you recall, the number of heads, 0, 1, 2. If I define it, this one corresponds to 1/4, this one corresponds to 1/2, this corresponds to 1/4. Then each of these is greater or equal to 0. All right? For all x, this is x1, x2, and x3. Then sum them up, sum all this is equal to 1. Now, but if I define another one, f of x equal to 1/2, 1/3, and 1/6. All right? Oh, no, this one no good because this 3, 2, 1. 3, 2, 1. It still add up to 1. Okay, let me change 1/4. All right? Now, if I give you a function f, I claim it to be probability function, and then define for 0 is 1/4. For 1, it is 1/3. For 2, it is 1/6. Each of these probability, this f of x1, f of x2, f of x3 are greater or equal to 0. But they don't add up to 1. What does it mean? It means that the way that we define this probability function is not correct. All right. So make sure that they add up equal to 1. Add up equal to 1. Add up what? Add up all this probability corresponding to the whole set of values for this random variable. All right? Remember, it's all the x, x1, x2 up to x infinity. All right? Okay, here's an example. I toss a coin. All right? X is the number of heads. So this is a probability. All right? So you can check. So all this greater than 1 and the add equal to 1. And if you plot, all right, these are the x value, x1, x2, and x3. These are the corresponding f of x. So this is a probability graph. So the graph, x-axis are the value of x. The y-axis is the probability. All right, so this is a line graph to show you how it behaves. In fact, from here you can tell the probability is the highest when x equal to 1. And it's less when x equals 0 and x equal to 2. And in fact, it's also symmetric about x equal to 1. All right? So we can have, instead of line, we can have histogram. So here is a graph, histogram. All right? So, so the probability of x equal to 1 is equal to this area. What is this area? This is half. So the height is half. And what's the width of this rectangle? From 0.5 to 1.5. So this is 1. So the area of this rectangle, which represents the probability of x equal to 1, x equal to 1, is equal to half. 0.5 or half times 1. And what is this probability? What is this area? The height is 1/4 and the width again is 1. So it's 1/4. So what is the total area of all these rectangles? 1/4 plus 1/2 plus 1/4. So it is 1. It is 1. So the point is the probabilities, all right, if you use the width 1, the probability for all these rectangles should add up equal to 1. Should add up equal to 1. All right. Okay, here's another example. So again, throw a pair of fair dice. Let's look at the sum. So here is the probability function. Each x values corresponding to it, we also have the probabilities. All right. So these are the xi, and this is the f of xi. This is what I call it xi, and this is x1, this is f of x1. All right, so check. Everyone is bigger or equal to 0. And the sum of all this equal to 1. So in other words, the probability distribution is well defined. Another example. We have 6 lots of components and ready to ship by a certain supplier, and the number of defective components for each lot is given as follows. All right. Now, the lots label by 1, 2, 3, 4, 5, 6. It's just a label. But for lot 1, there are no defectives. Lot 2, there are 2 defectives. All right? Okay? So, now, let's define one of these lots is randomly select and for shipment to a particular customer, and let X be the number of defectives in the select lot. All right? So, now, is X a random variable? Is X a variable first? Is that a variable? Yes. It can take the value 0, 1, 2. Right? Is it a random variable? Of course it's random variable. If you select lot 1, X equal to 0. If you select lot 6, X also equal to 0. So here it is. Now, X takes the value 0, 1, and 2. All right? Here's the equivalent event. When will I get a lot, and then get the number of defectives is 0. The bat has 0 defectives. So it's equivalent to I select lot 1 or lot 3 or lot 6. So in other words, the chance that I got X equal to 0 should be 3 over 6. 3 over 6. Am I right? And this makes use of the idea of equivalent events, where X equal to 0. When there are no defectives, the lot that you choose no defective, which is equivalent to either you choose the lot 1 or lot 3 or lot 6. All right? So you have to combine them, so the chance is 3, 6. All right. So this is how we obtain the probabilities. All right? So now, these are all possible values of my random variable X, which represent the number of defectives. These are the probabilities associated with those numbers, and each of them are bigger or equal to 0, in fact bigger than 0. At the same time, this all add up equal to 1. Equal to 1. So it's a well-defined probability function. All right? Another example. Find a constant C such that this one is a well-defined probability function. Now, so far I did not mention this part. This is important. So I make sure that I cover all the numbers. If X equal to 1, 2, 3, 4, then I use the formula. If X takes value other than 1, 2, 3, 4, let's say 1.5, let's say 10, then the f of X, that means the probability, is equal to 0. That's what 0 otherwise means. So if X takes other values, then the f of X should be 0. So this part, a lot of time we ignore it, but you better put it back. All right? So I want this to be a probability function. So in fact, so we make sure that f of X is bigger or equal to 0 for X equal to 1, 2, 3, 4. And also f of X sum up equal to 1. All right? And after that, we have to find the probability of X greater or equal to 3. All right? So we use this one first to figure out C plus 2C, because X1 means X equal to 1, X equal to 2, X equal to 3, and X equal to 4. So it's C plus 2C plus 3C plus 4C equal to 1. So C equal to 1/10. All right? Which means that if C takes the value 1/10, then the probability, all these probabilities should sum up equal to 1. All right? Now don't forget there's another criteria that you have to check. But luckily, this is automatically fulfilled. You need all the f of x to be bigger or equal to 0. So if after you solve the formula, you find C to be negative, then you're in trouble. All right? Here C is 1/10, so all the f of x are bigger than 0 because it's 1/10 times 1, 1/10 times 2, 1/10 times 3, and 1/10 times 4. All these are positive. All right? So to find the probability of x greater or equal to 3, which is equivalent to probability of x equal to 3 plus probability of x equal to 4. In fact, strictly speaking, this means that it's probability of x equal 3 or x equal 4. Right? Bigger or equal to 3 means can be 3, can be 4. Can it be 5? If you want, you can put it down, but probability of x equal 5 is 0, so we ignore it. All right? What I'm trying to say is that, strictly speaking, this is supposed to be all x equal to 5 or x equal to 6. Wow. Right? X bigger or equal to 3 means this one. Right? Then can I write this as probability? Can I do it like that? Oh. Huh? Are these two the same? Are they the same? Yes? No? They're the same. Why they're the same? Because they're mutually exclusive events. Why are they mutually exclusive? If you got x equal to 4, can it be 5? Cannot be. Can it be 3? Cannot be. You can only take one value. All right? All right? So, it's mutually exclusive. Okay? So this is equal to this. But all these are 0. You don't have the probability. It's 0. So it's equal to probability of x equal to 3 plus probability of x equal to 4. So the answer is 7/10. Right. Why I'm so long-winded? I want you to understand how to get the answer, not just by manipulating the answer. So ask x greater or equal to 3. In fact, it's equal to x equal 3, x equal 4, x equal 5, or x equal 7, and so on. Infinite number of them, which can be translated into sum of the probability because they're mutually exclusive. Then the probability of x equal to 5, x equal to 6, all this equal to 0. All right, so it reduced to just probability of 3, x equal to 3 plus probability x equal to 4. Oh, yeah. I still have 1 minute, right? Or 5 or 6 more minutes. Last example, I have to go a little bit over time. Okay, example 5. Okay, we consider 5 potential blood donors, A, B, C, D, E, of whom only A and B are O positive. 5 blood samples, 1 from each individual, will be typed in random order until an O plus individual is identified. All right? So let Y be the number of typing necessary to identify an individual. So, Y. What are the possible values for Y? You must test at least, okay. So Y is in this set 1, you take 1. And happens that you select the one with O plus, then you stop because you already identified 1. All right? Or 2. Or, can it be 3? Huh? Can it be 4? Do you need to identify, you check 4 of them before you get the first O plus? Okay. Okay. Now, let's start with Y equal 1. It means that you already got one of them, A, B, all right? A or B. So the chance is 0.4. Then Y equal to 2, which means that you have to select C, D, E in the first one. And then after that, you select A or B. Now here I use the counting method. So select 1 out of the 3 times select 1 out of the 2. This is 2 represent AB, this 3 represent C, D, E. So this is a possible way of get them. Alternatively, you can think of it, the first one, you have 3 over 5 to select. Right? Yeah, they will learn. All right, next time it will not come so early. 3 over 5. Then this is 3 non-O plus out of 5. Now after that, I'm left with 4. And out of this 4, AB is still there. So it is 2 over 4. So the same as this one. So the answer is 0.3. All right, so it's F1, F2. Do we have F3? Huh? Of course we have F3. We can have the first 3 are non-O plus. So this is the counting method. If I use the conditional probability, it will be the first one is non-O plus, 3 of them out of 5. After I select one non-O plus, left with 4. Out of this, how many non-O plus are there? 2. All right? Now these 2 refer to non-O plus. Then after that, I left with 3. And how many non-O plus? 1. Then after that, I'm sure the next one, it will be 2 over 2. All right? Left with 2 persons, both of them are O plus, so of course. All right? So we'll have. So this part you can ignore it. All right? So we get the answer, 0.2. Oh! What do I 4? Oh. Okay, 4. Let me check. How come? AB are positive until O positive is identified. So 0.4, 0.3, and 0.2. Oh. Two choose one. Oh, yeah, of course. Gee, I lost. Yeah, this is exactly what we are doing. All right? Of course. Right? So, this part, all right, is how you get to 4. This part, also how you get 3. All right? Not this one. No, sorry, wrong. So this is referring to this part. All right. So for other values, 0. You don't need to go to 5. So adding up equal to 1. Adding up all this probability equal to 1. All right. So you can use counting method as what I show in the lecture notes, or use the conditional probability. Maybe conditional probability easier, all right? Easier to work with. So make sure that the probability function is a positive for the probability, and they add up equal to 1. And make sure that outside this, all right, they're defined as 0 probability. Okay, so I think I have to stop here, all right? Okay, see you on Thursday.